Alright, heck yeah, we're doing it. And, man, what the hell we doing? Well, we're doing this. Anytime you see, like, VDV, what the hell is that? And just getting to it, you know what I mean? dx dt, well, that's velocity, but guess what? That's dx dv times dv dt. You're like, what? Okay. Like, I don't know what you're doing, but whatever. And then you can also do, like, if it's polar coordinates, dx dt, this might be dx d angle times d angle dt. You know what I mean? You're like, I don't know what that is. That's why I just make the joke. It's just like, whoa, it seems like you can just put anything in the middle. You know what I mean? dx d McDonald's. You know what I mean? D McDonald's dt. You know, it's called like differentiation, and it's like I forget even what the term's called. But we're gonna try to get there hella fast. We got to start with the basics. Okay, so the definition of velocity is change in position, that's x, change in time. See, there's many ways to write change, you know, change in, you know, this could be written change in x as well. It's x2 minus x1. That's also x final minus x initial. You're like, oh, that's also this little caret. I don't know what that called. It's just called the change symbol. I don't know what Greek crazy letter that is. It's probably like a Greek A. Who knows? But that's change in x. Alright, change in time. Same thing. T2 minus T1. Change in time might be time final minus time initial. Or it just might be this little thing, T. But guess what? It took me graduating college and then not caring for 20 years and then starting to care to be like, oh, are you kidding me? When you see this little dx, like, that's all they were talking about? dx, this little thing, dx, we see this all the time. We see dt, hell, I see that all the time in integration. I don't pay attention to it in differentiation because I don't know what the hell's going on. You know what I mean? But you're saying, whoa, this little dx means this little symbol x. That means x final minus x initial. That means x2 minus x1. That means change in x. Yes. And no. Well, don't confuse me. But yes, for all intents and purposes, anytime you see this little dt, hell yeah. You know, it's a change in time. It could be 1 second. It could be a million seconds. You know, who cares? But definitionally, this says, hey, we're trying to make this as small as possible. You know what I mean? It don't need to be as small as possible, but it needs to be as small as possible if your guess is going to be accurate. Well, you know what I mean? But it can be real big. It can be decently big if you just want to be like, I mean, you might only be off by 5%. 5 to 10% error. You know how many problems that I just got like 1,000% error? I wasn't even in the right, you know what I mean, Wrigley Field. Holy Toledo. So yes, this does mean your change in t is like infinitesimally small. Your change in x is infinitesimally small. And that's what they drilled into my head. That's what it messed me up. It's like, no, don't think that way. Yes, it is an infinitesimally small change in x, infinitesimally small change in t. But guess what? No, as in, hell, make it as big a change in x as you want. Make it as big a change in t as you want. And guess what? You'll probably get the right answer. Decent enough. Okay, so this is also cool because... Alright, let's say so this is velocity. Let's say I'm going 60 miles per hour. What the hell do we know about this? Let's say there's a town that's 60 miles away. So you don't even need to use your head. time. How long is it going to take to get to that town? Hell yeah, 1 hour. Okay, perfect. Let's say I'm going 60 miles per hour. Kinda same question, but let's say I drive for an hour. Whoa, we've been driving for an hour? Whoa, that's a long time. So now, X, how far have you gone? Ooh, we can all do this. 60 miles per hour times 1 hour, except that gal on the internet when her boyfriend's just like, hey, if we go 60 miles an hour, how many miles do we go in an hour? She couldn't figure it out, but that's a trick question, you know what I mean? It's just set up to be tricked. But anyway, 60 miles per hour, going 1 hour, we're going 60 miles. I'm going to mess up. I'm going to write like 2 miles, 1 mile. But anyway, so yeah, so booyah, TX. Okay, and then let's just figure it out. Like, what was our change in T? What was our DT? What was our T2 minus T1? What was our T final minus T initial? How many other ways, like what was our change in time? How many ways can we write times changing? How about this? What was our, change in position, change in X? What was our DX? What was our X2 minus X1? What was our X final minus X initial? Let's say this was just X, Z minus X, Y. I don't know why I did that, but maybe, this might be the 222nd term minus the X 221st term. It don't matter. It might be X0 minus X to the -1, you know what I mean? If this is 0 seconds and -1 second, I don't know how you'd have that, but this might be X 0 degrees minus X -1 degree. Okay, it's change. It's the change in X. You got to take the final position minus the initial position. Final position minus initial. You get any other, yeah, and then I think we wrote them all. But you can also write just change in X. It's so darn important. And what is this? What is our DX? Well, it's 60 miles. What is our DT? Oh, it looks like it's 1 hour. Okay, what's the definition of velocity? Right now, we know that the definition of velocity is the change in X, change in position, divided by the change in time. Whoa, okay, our DX is 60, and our change in time is 1 hour. Okay, and this is, 60 miles. So now we got 60 miles per hour. Okay, our velocity is 60 miles per hour. Now, is that true? Yes. Is that not true? Yes. Is that true and not true at the same time? Yes. Okay, yeah. Because your car was in the driveway. What was its velocity? It was 0. When you got to the next town, what was the velocity? It was 0. 0 miles per hour. Miles per hour. Okay, but you just said your car was going 60 miles per hour. Yeah, pretty much for the entire trip. Okay, but let's say you actually did your top, this is where you actually get in, whoa. If my top speed was 60 miles per hour and I drove for 1 hour, but I started from a stop and I ended at a stop, how many miles could I actually travel? Like theoretically, I mean actually. Well, it takes 6 seconds. It might take a whole 10 seconds to get up to 60 miles an hour. It might take a whole, it might take maybe 15. It might take a half a minute to get up to 60 miles per. You know what I mean? Anyway, so you're gonna go less miles. You're gonna go like 59.9 miles. You know what I mean? Because it took a little while. Anyway, that's why even if you just have DX, this thing better be like kind of small sometimes, but it's all right if it's huge too. Okay, because this car didn't change velocity too much. But if you really want to know what the velocity was like after it started up, like 1 second later, you know what I mean? Then it's going to be different. Okay, I don't know if that's what I wanted to get at, but you got this velocity, which is change in position, change in time. Okay, and But check this out. We got three terms. We got the velocity term, we got the change in x term, change in position, and we got the change in time term. So let's say this is just equation 1. Well, guess what? We can have, let's just do equation 3. I think that'll make the most sense. Because what if we just want to find the change in time? You know what I mean? Didn't we say back here that if we were going 60 miles per hour, so we knew our velocity and we knew our change in x. Okay, we were going 60 miles per hour and we knew that our change in position was 60 miles. How do we find our dt, our change in time? Or just time, you know what I mean? Well, look at this. You bring this upstairs and you bring this downstairs, you know what I mean? And so you got change in time is equal to dx over v. So this is the cool thing about physics, engineering, math. If you got one equation with three things going on, that means you got three equations because you can just rearrange them. So yeah, if you ever wanted to find, if you know it was 60 miles to the next town and you're going 60 miles per hour, you can calculate your time. Cool, it was an hour. Or if you want to calculate your velocity, hell, that town's 60 miles away and it took us an hour to get there. Whoa, it looks like you were going 60 miles per hour. Okay, well, what's the second equation? Well, changing, so you dx, you're changing position. We can figure out how far we went if we take our velocity times change in time. If we take our velocity times dt, our change in time, well, let's figure it out. I know my velocity is 60 miles per hour. My change in time was 1 hour. What was my change in position? 60 miles. Whoa, so that's like literally you can turn the video off right now because, whoa, like this is getting you started to be like, oh, okay, I get it. Like if you got one thing going on, like you got three things. Okay, because back up right here. You're like, what? Like, okay, so you have dx dt. This is the one that we did. We figured out all three equations of this. But then you were saying that, yeah, change in position over divided by change in time. Yeah, that's velocity. We all know that. But what the hell is this? Change in position divided by the change in velocity? What the hell is the change in velocity? And now I need a new sheet of paper. So I'm going to catch you on the flip side. Alright, hell yeah, we're back, and we said the definition of velocity was change in position, change in time. And then we got three equations, because we could also say, the change in position is equal to the velocity times the change in time. And we can also say the change in time is equal to the change in position divided by the velocity. Okay, cool. But what they were getting at was velocity is change in position divided by change in time. But, this is equal to change in position divided by change in velocity times change in velocity divided by change in time. You know what I mean? And you're like, what? So this is where you're like, what? But now we need another equation. So if velocity is change in position divided by change in time, guess what? Guess what acceleration is? Acceleration is change in velocity divided by the change in time. Perfect. So we have equation 1, equation 2, equation 3. And we're going to say this is equation... Yeah, I think we get it. So now here is another equation 1. And guess what? We're going to have 3 more. So what did we do here? We said velocity is equal to dx dt, change in position, change in time. And never say dx dt. Say change in time, change in position. It just makes it so much better. And then the second one, see, we solve for change in position. So we're going to solve for the second one. We're going to solve for this. Change in velocity is equal to acceleration times change in time. Okay, fair enough. And we're going to see if any of these make sense. And then we can solve for change in time. Change in time is equal to, back here, upstairs, downstairs, change in velocity divided by acceleration. Whoa, and maybe, maybe you can just do an amazing thing. You're saying that these change in times are the same? Well, if these change in times are the same, that means change in position divided by change in velocity is also equal to change in velocity divided by acceleration. I don't know. We just came up with a new one. You know what I mean? You're like, this is true. This is so true. And let's spend 2 minutes proving this. The easiest way is if you have a rock that's fallen from the sky, gravity is 9.8 meters per second squared. What the hell is that? That's 9.8 meters per second. And you're changing your velocity. Change in V by 9.8 meters per second. Well, isn't that dV dt? Yes, it's change in velocity of 9.8 meters per second in 1 second. dV dt. Acceleration. dV dt. That's what we have. That's equation 1. Okay, cool. And just to let you know, if you integrate acceleration with respect to time, dt, you will get velocity. So now we're going to integrate 9.8. This is just a number, but it's constant. So it is an equation. And you can just go t to the 0. That's 1, but now dt. But now when you integrate, you'll get 9.8t, t to the 1, 0 plus 1, this is common integration, plus a constant. And this is your velocity. But guess what? If you're dropping a rock from 0 velocity initial 0. Okay, so this is 0. Perfect. We got our first equation. Velocity is 9.8t. Let's get our second equation. We're going to integrate velocity, dt. That's going to be 9.8. That's going to integration 9.8t to the 1 dt. Well, that's 4.9 t to the 1 plus. If you do it like normal, that's 9.8 t squared integrating, or no, that's 1 plus 1 t to the 1 plus 1 divided by 1 plus 1 plus c. We're doing all the dots, connecting all the dots. And this is velocity. So what's our, this is our position. Well, integration of velocity dt is position. Okay, and what's our initial position? We're just going to say this is 0, 0. 0, 0 coordinate system. Okay, this is 0. So we got, and this is 2 right here. So we got 4.9 t, this is 2, t squared. Okay, we got our equation. So we got acceleration, 9.8. Velocity is 9.8 t. Position is 4.9 t squared. All right, and we're going to do position initial. We're going to do at 0 seconds, like right at the beginning, and then at 1 second, and that's going to be our initial, and this is going to be our final. Okay, position initial at 0 seconds. So t is equal to 0 seconds. T is equal to 1 second. That's going to be our final. Well, position is 4.9, 0 squared. Okay, our initial position is 0 because we put in 0 seconds. Now x final, well that's, so another way to write this. This is x t equals 0. This is x t equals 1. This is initial final. This might be x1. This might be x2. You know what I mean? Oh, okay. Well, so now can't we find dx? Because didn't you say dx was just all that jazz? x2 minus x1. It's also x final minus x initial. You know, hell yeah, we can find dx. Cool. Cool. Okay, and isn't that what we're trying to find down here? Hell yeah. Okay, so x final when t is equal to 1 second. Well, that's 1 squared. That's 1. So it's 4.9. 4.9 meters. Okay, cool. Oh, and then what's our definition for velocity? Okay, let's go back up here. So, you know, look at this cheat sheet. Just all these are just super relevant. You need all of them. There's 6 equations here. Literally, there's 6 equations. Who knew just one number? Even this number, 9.8. Well, that's a dv dt. Hell yeah, look at that, look at that, look at that. And it's a 9.8 meters per second. That's your change in velocity. Change in time, 1 second. Whoa, who knew? Who knew like this was, like, hey, that's your acceleration. 9.8. Your change in velocity, that's that. So here's your acceleration. Here's your dv. Here's your dt. Whoa, so even just one number is like is 3 things, and it's an equation because with respect to time, it's t to the 0. No matter how much time this rock falls through the sky, gravity, well, within reason, it's going to change if you go up to really high elevations. But, you know, if you throw it off of a building or a dam or something, a cliff, gravity is 9.8. And it's going to be that way in forever. Even when that rock hits the ground, guess what? Guess what gravity is? 9.8. So anyway, we get it. Oh, but didn't you say acceleration is change in velocity, change in time? So what happens when that rock hits the ground and it's just stopped? Well, then what? Well, then you need Newton's equation, and we'll prelude to it. The force on the ground that is needed to actually hold that rock in the universe on the Earth's surface is equal to ma. It's the mass of the rock times acceleration. What's the acceleration? Well, that's gravity, not the thing that don't change. Whoa. You're saying the force that's required to hold that rock on the surface of the Earth for all eternity is equal to the mass of the rock. Maybe it's a 1 kilogram rock times 9.8 meters per second squared. How many newtons is that? Well, that's going to be 1 newton. 1 newton of force. No, I totally did that wrong. No, that's going to be 9.8. That's going to be 9.8 newtons. Because, okay, so unit-wise, 1 newton is equal to 1 kilogram times 1 meter per second squared. Gravity's hella. Gravity is pretty serious. It's like 10 of these. You're going to get 10 newtons. Yeah, that's about 2.5 pounds. Because 1 newton, that's a quarter pounder at McDonald's. That's a quarter pound. You know what I mean? Just think McDonald's for all this stuff. That looks like an upside down butt or something. Okay, well, let's get on with it. So yeah, back to this one. We kind of just made up this equation because we got 6 little equations, and you're just like, whoa, those are the same. Those are the same. Well, let's put them together. Okay, so back to it. And man, we might need a little bit more space, but we're doing it. How many did we get? We got change in position. Yeah, from 0 seconds to 1 second. We got change in dx is equal to 4.9 meters. Did I even write that out anywhere? Dx is equal to, 4.9 minus 0 meters. So that's dx is equal to 4. Let's write it out. Dx, 4.9 meters. Got that. So we got that component. Our velocity. Now, what the hell? Well, what's our velocity? Well, now you got to put on your thinking cap, because look at this. Look at this. When you dropped the rock, it had no velocity, and then it had some velocity at 1 second. So let's figure that out first. What's our change in velocity? Okay, so our velocity change, dv. Yeah, dv is equal to velocity final minus velocity initial. It's velocity 2 minus velocity 1. It's a dv. It's what else can we do? It's this little thing, you know what I mean? Little change in sign v. Okay, and what's that? Well, here's our velocity equation. Velocity when time is equal to 0, well, our velocity is 0. Velocity when time is equal to 1 second, well, it's 9.8. So our velocity, our change in velocity is 9.8 meters per second minus 0 meters per second. Our initial velocity, velocity initial, velocity final. Oh, okay, so our change in velocity is 9.8 meters per second. Cool. Cool. Okay, so now we got our dv. And this is dv. Well, didn't we say v is equal to change in dx dt? Yeah. So what's our dt? Well, oh, we already figured that that's 1 second. Okay, so our dt is 1 second. So we got that. Booyah. And that means our velocity is change in position, 4.9 meters, because that was our dx, divided by 1 second. See how this is dx dt? Velocity, dx dt. And so our velocity is 4.9 meters per second. Now this one you might be like, what? Why is our velocity 4.9 meters per second? Because when we calculated our change in velocity, it was 9.8. Because this is an average. This is for sure an average. And this is an average. And these are functions. These are functions. You know what I mean? See back here, acceleration is a function of velocity, is a function of position, is a function of time. Same as velocity. Velocity is a function of position and time. You know what I mean? It might be a function of an angle. You know what I mean? It might be a function of your Big Mac and McDonald's. You know what I mean? So that's why I do the... That's not how you do it. The arches isn't like an upside down butt. McDonald's would have gone nowhere if that was their symbol. If that was the symbol for McDonald's, you'd be like, no, that just looks like a butt. And maybe that is the symbol for me. I don't think so. I think the symbol for McDonald's is like that. And then I think it's like that just to make, yeah. I don't know. Maybe the symbol for McDonald's is just a little butt cheek. But anyway, but see, so here's the second take home. You can stop this video now again. Oh my God. Okay, Fuya. I only got 20 minutes on this camera, and oh, I hate it when I go. All right, so we got another 20 minutes on the clock. Whew, that scared the life out of me. I even got to set an alarm. Set 19 minutes. Hell yeah. Because I just get on a roll. And yeah, so the take home, you can stop this video now because you're just like, oh, I get it. This is the change in x. This is the change in velocity. But this is going to be your average velocity. This is going to be your average acceleration. When it comes to gravity, it don't change. It's literally a constant. But velocity, no, that's changing. That's changing. It's changing with respect to time. Velocity is a function of time for sure. And what was our equation for velocity? Yeah, we had 3 equations over there. We go. Equation for velocity, function of time. Equation for an acceleration. This is also a function of time right there. And well, this is acceleration as a function of position is also 9.8 meters per second squared, because it don't matter what position you're in. This rock could be anywhere. And acceleration, like we said, gravity is always the same. So acceleration as a function of time is the same too. 9.8 meters per second. But velocity as a function, this is velocity as a function of time. How would we do, and I need, I'm just going to put this, man, what are we going to do? Just put this right here, and then just draw a line. Yeah, because what we want to know, how about velocity, and we'll just skip right to that. How about velocity as a function of position? What the hell does that mean? Well, it says, when I drop this rock, I want to measure 10 meters, and I want to know what the hell the velocity, I want to measure 9.8 meters, and I want to know what the velocity is. Well, didn't we just do that? We said our dx. Oh, no. Our change in, I want to measure at 4.9 meters. At 4.9 meters, I want to know what the velocity is. What's the velocity at 4.9 meters? Didn't we just do that? Didn't we say the velocity using this equation was 4.9 meters per second? Yep. And but we used this equation because we knew the change in time mainly. And then so here's how you do that real fast, just so you're not stumped. You take the position equation, And see how the position equation is 4.9 t squared? We'll solve for t. And then that's going to be x divided by 4.9 square root. Okay, and now go back to your velocity equation. This was velocity as a function of time, 9.8 t. But now substitute these in for each other, and what we'll get the velocity as a function of position. Holy, it's that easy? 9.8 square root of x over 4.9? Yes, because now we want to know the velocity at x equals 4.9 meters. You know, you might see it velocity at 4.9 meters. Anyway, or just velocity at x equals 4.9 meters. And that's going to be, any of these is going to be 9.8 square root. The x is 4.9 meters divided by 4.9. Okay, that's the square root of 1. That's 1. All right, so our velocity is going to be 9.8 meters per second. Well, isn't that what we got? Hell yeah. Velocity, 9.8 meters per second. There you go. Velocity, 9.8 meters per second. Booyah. All right, so now we found the dv right there, dx. There you go. And what's our acceleration? Like we said, our acceleration was just always a constant. Acceleration is a function of position, 9.8 meters per second every second. Acceleration is a function of time. Well, 9.8 meters per second every second. That's meters per second squared. That's change in velocity, dv dt. That's change in 9.8 meters per second every change in 1 second. Many ways to write this, and you got to write it 1,000 different ways. Alright, holy Toledo. So the other aspect of working with this camera is the battery can run out of juice. So yes, so we got down here and we said that acceleration is a constant 9.8. So then we're done. All I did was this, but we came back to our equation. dx over v is equal to dv over a. Where did we get that? Because we came up with, we said that the change in time, these are the same thing, so we can make them equal to each other. So then we just rallied the troops, you know what I mean? What's our change in position? That was 4.9. So I was just like, okay, change in x, 4.9. What's our velocity? 4.9. What's our change in velocity? 9.8. What's our acceleration? 9.8. Let's plug them into this equation. Hell yeah. So if you do that, 4.9 divided by 4.9. 9.8 divided by 9.8. Hell yeah. So that's going to equal 1 over, so it's going to be 1 is equal to 1. And then I actually went back and be like, well, 1 what? So I was just like, what the hell is the units on here? So I said, well, change in x, that unit is meters. Velocity, that's meters per second. Over here, change in velocity. Well, that's just velocity, meters per second. This is acceleration, meters per second squared. Okay, so what's a meter divided by a meter per second? Well, these cancel, but then this comes upstairs, and you're just left with seconds. So, cool. So this side is equal to seconds. How about this? Meters per second divided by meters per second squared. Both meters cancel. One of the seconds cancels, but then you have, because this is meters divided by seconds, the seconds isn't down here, it's actually up here. So we got seconds is equal to seconds. And that should make sense because we said, hey, this was dt is equal to that. Change in time is equal to that. We can make them equal to each other. Oh. So then I went right here. So, dt is equal to dx over v is equal to dv over a. See, these are all the same. Change in time is equal to all that, So, yeah, this is all equal to 1 second. All right, sweet. And then I was saying, yes, perfect. So this is a full equation. We can use this if we ever needed to use this. Anytime that you have acceleration, I don't know, maybe you want to throw all this junk in. And let's just do it real fast, right here. Let's say I want to solve for acceleration. I'm going to bring acceleration up top over here. and then I got to move all that crap. So we got acceleration is equal to dv, v dv divided by dx. Oh, sweet. So we got another equation. Let's say I just want to solve for velocity. We got to move that upstairs, and then got to get that downstairs and that up. So velocity is equal to acceleration dx dv. Okay, we got another one. And so we just solved for A, we solved for V. You know, we could do two more. You know what I mean? And I'm sorry, so dx is equal to, well, v dv over A. And then dv is equal to A dx over v. So we have four equations. So from this four, we got 5, 6, 7, 8. You know what I mean? 5, 6. Yeah, anyway. Yeah, there you go. So from this equation, hell yeah, you get 4 more equations. And they might be useful. And now we kind of know what's going on. This is actually an average, or it's the function. Average or the function, average or the function, average or the function. This is, hey, we did take a slice in time, and we found the change in velocity. And we did take a slice in time, and see, you don't have dx here, but dx is implied, because we don't live in a universe where you can change your position and do that without changing time. That's Doc Brown type stuff. You just invented the DeLorean. If you could change your position, if you were here and then you went over here and you did not change your time, that's Doc Brown, baby. You know what I mean? Tell me what you're on, because we all want a piece of that. You know, inject that in our arm if you found a way to get from here to there without changing your time. So see how change in time is implied? Yes. So, okay, so that's pretty cool. I'm going to write these out, and then we're going to get a new sheet of paper. Catch you on the flip side. All right, we're back at it. And, all right, so, let's see. Okay, so I got all of our equations in. Our velocity, change in x, change in t. Acceleration, change in velocity, change in time. And then, what did we say? We say we can solve for change in time. Let's get this in here. We can solve for change in time on both these, and you can get dx over v is equal to dv over a. And that gives you, like, you know, at least 4 more equations. But then I was thinking this also gives you can flip-flop these. So then you can get, you know, you can get V over A. V over A is equal to dx over dv. Okay, so yeah, fair enough. So that's another one you can do. And it'd be the same if you did it the other way. Yeah. Okay, sweet. So that really does give us, I think that's another one. I think that would be 9. Okay, so back to this one, though. This is the chain rule of differentiation. Chain rule. We got velocity is equal to change in position divided by change in time. Change in position, change in time. But you can say dx dt. You can say this is equal to dx dv times dv dt. Because these can cancel out, and then you're just left with dx dt. But for the love of God, I've never understood, you know, like what's the practical purpose of the chain rule, how it's useful. But I think it can be useful if we actually go on to figure out what the acceleration is. Because acceleration is dv dt. And now you can do something kind of interesting. Is this the one you want to do it to? Holy Toledo. Did we ever solve... Okay. I think they just do this. I think they say, hey, this is V, and look at what all this stuff is. You know what I mean? So, you would have... you would have D... see, that's interesting. I never understood the I actually need to go back and figure out how to do differentiation. And then the chain rule. Because if you have... because yeah, you could do this. You could go d dt and then a big parentheses and then just write all this stuff in. dx dv, dv dt. And you can write all that in. And for some problems, that's useful. Classically, though, let's say it is a circular problem where you're just like, whoa, you got something, this is your path of your line, and then you have an angle theta, and then you have position, and then you got a position. And you're trying to find out so if your velocity is equal to dx dt, but you can do dx d theta, what the hell is that? Yeah, d theta, so d angle d theta dt. And then this, the change in your angle divided by the change in your time. Well, the change in your angle is just omega. That's going to be either radians per second or omega is degrees per second. Typically, it's radians per second because that's useful because if you take radians times radius, so if you take this times the radius, you'll actually get the velocity. That's another equation. If you take this omega r, if you take degrees per second times the radius, you do not get the velocity. You do not get the velocity. You have to take radians per second times the radius, then you'll get the velocity. Okay, but this is just omega, so you can simplify this to dx d theta omega, and then sometimes that's helpful because now let's say you have a function. Your function of x is just sine theta. Okay. Do we know what sine theta is? This is where all the pro teachers are just like, well, draw a damn graph and throw in, and then what? This is your angle, and then this is going to be your f of x. So this is going to be your sine theta. So, okay. And then when theta is 0, what's sine of 0? Well, that's 0. So right there, booyah. When sine is 90, well, that's going to be 1. Okay, so yeah, booyah. So here we're just going to go 90 degrees. And this is 1. Okay, perfect. And then what else do we know? We know that if sine is 30, well, that would be like a third of the way. When sine's 30, sine of 30 is 0.5. Oh, okay, so it's like halfway. Oh, look at that. So you kind of got a straight line over here. Does it go down here? Hell yeah, it does. Because, and then guess what? Small angle theorem says sine of 15 is, so if sine 30 is equal to 0.5, sine of 15, because small angle is just half that, 0.25. Okay, so right there. And then half that, sine 7.5 is half that. Okay, and then half that. Okay, so yeah, you get, this is your sine graph. Okay, there you go. And we did it, but we should have done sine 60, because sine 60 is 0.8. It's actually, so if this is 6, 7, 8, 9, it's 0.866. Yeah, we pretty much got it. Okay, so there's your sine. Okay, so and now let's say this your function is just your position along here, because this is what you're doing. Okay, so what's your so now you want to know the change in position with respect to theta. So what's dx d theta? Well, if this is x, you just write this whole thing in here. So you go d sine theta d theta. So what you're doing here is you're saying, let's pick 2. You know what I mean? You got 30 degrees here and you got 0.5. And then I said you got 60 degrees and then you got 0.866. Okay, so let's do it. Your x changes. Your x1 is equal to 0.5. Your x2 is equal to 0.866. Your theta 1 is equal to 30. Your theta 2 is equal to 60. Alright, so your d theta is 30. And your dx, well, that's like a 0.866 minus 0.5. That's a 0.366. Okay, so now you just found dx d theta. That's all we were trying to find. Dx d theta, well, that's going to be 0.366 divided by 30. 0.366 divided by 30. Okay, dx d theta is 0.0122. Okay, fair enough. So, if someone's like, and let's say that's just for, yeah. It doesn't seem right. Now I almost need to go to Excel to actually do this, because what I wanted was dx d theta, and x we were saying was sine theta. And if we change this up, we're gonna get, yeah, you're basically just differentiating. What's the differential of sine? Well, let's just figure it out. So look at this. Look at this. So right here, it's steep as hell probably, and it's going to be cosine. So right here, the differential dx d theta, the change in sine right here divided by well, it's going to be real high. Well, let's figure this out. Let's figure this out, because at 30 degrees you got 0.5. At 15 you got 0.25. At 7.5 you got 0.125. And then at 7.5 divided by 2, this is the last one we'll do, 3.75, you got 0.0625. So here's your dx and here's your d theta. D theta is 7.5 minus 3.7. Yeah, your d theta is 3.75. And then your dx, 0.125 divided by 0.6625. Yeah, your dx is equal to 2. Okay, so dx d theta is going to be 3.75 divided by 2. 3.75 divided by 2. Yeah, it's going to be 1.875. So it's going to be kind of steep. It's going to be just like that. Booyah. And I think that's what we see. In between 7 degrees and 3 degrees and 7 degrees, yeah, that's going to be right there. And what the hell did we say this was? Well, we said that was pretty. That don't look like that. So what did we make a mistake? Well, let's see if we did. Well, let's take let's do this one. So you got 15 degrees. That's your d theta. Dx is 0.25. Okay, so dx d theta is equal to 0.25 divided by 15. 0.25 divided by 15. That's going to be 0.016. So that's real small. I don't think that's exactly what we get. Well, let's just do it. So what's cosine of x? Graph that out. We're going to zoom fit this puppy. And then we're going to take the value of it. Value at 0 is 1. value at 30 is 0.86. Yeah, so, damn it. Holy Toledo. So there's a way to do this where, well, let's just take a little pause. So you have sine theta. And we're going to go sine of 31 degrees. And then we're going to go sine of 30 degrees. So sine of 31, stored as alpha, we'll do A. And then sine of 30, stored as alpha, oh, we got to store that as alpha A. So sine of 31 stored as alpha B. And we're going to go alpha B minus alpha A. That's going to be our dx. And our d theta is 1. So dx d theta is equal to 0.015. So maybe I'm totally doing something wrong. I feel like I'm doing something wrong. You know what? I think it's because this angle needs to be in radians. I think that's kind of the issue we're running in here. And that's why sometimes degrees are just god-awful. Let's try that. Let's do mode radians. And then we're going to go, and we're going to do this. Sine of 30 and then 31. This is going to be A, B in our calculator. Dx, d theta is going to be, is B minus A divided by whatever the radians this is minus whatever the radians 2 minus radians 1. Okay, so 30 degrees in radians. Well, 30 degrees is this much of a circle times a full circle, which is 2 pi radians in a full circle, and that's how many radians? So 2 pi times 30 divided by 360. Yeah, it's like 0.5235 radians. Okay, perfect. Yeah, I think this is the only way to make this make sense. So we're going to store that as alpha r. And then we're going to go 31 divided by 360 times 2 pi. Store that as alpha s. Okay, so we have s minus r. And then we got to go sine 30 stored as a, sine 31 stored as b. So now we're going to go alpha b minus alpha a divided by alpha s minus alpha r. Perfect. And then we're going to get dx d theta is 33. So no, that don't help us out. Holy Toledo. I don't get... If our function of x is equal to sine x, then the change in x with respect... Oh, maybe that's where we're getting confused. Man, this is good because I don't know derivatives, you know. So we got up to the point where I don't know, and I'm still going to continue on with this because if we can figure anything out, that's going to be great. And I think I would like to go back here because we did our acceleration is 9.8, velocity is 9.8 t. And we have our position is 4.9 t squared. We also know that this is t is equal to x divided by 4.9 square root. And then that means that also velocity is equal to 9.8 square root x over 4.9. So perfect. So we have all these. Now dx dv oh, well, right here. So, yeah. So, you go dx dv. But what is this? This is dv dt. And then if we go over here to our equation, dv dt is just acceleration. So, I think that's kind of the first thing. Velocity is change in position, change in time, is equal to dx dv times dv dt, but this is just acceleration. So then we know dx dv times acceleration. Anyway, I'll have to go back to the chain rule of why this is useful. I mean, I guess let's just do the first problem here, because we're just really dragging our feet. And I don't know if the chain rule applies in here, but we'll just kind of use what we know to do kind of a complicated problem. So this one, you got to know, what's the whole point of finding accelerations? It's because F equals ma. And what the hell does that mean? It really means that if you have an acceleration, if you can identify an acceleration, that's important. Because if it's like an amusement park ride where you got people, you know, going in a circle, well, people can only handle 3 G's. You know, an acceleration of gravity is 9.8 meters per second squared, which is approximately 10 meters per second squared. So really, if you got an amusement park ride and you're hitting more than 30 meters per second squared, well, you got an issue, you know what I mean? Because the humans can only handle 3 G's. Okay, but the other cool thing about, so that's just, you know, hey, we need to find the acceleration. But the other cool thing about this is if you find the acceleration, well, the reason is because look at this. Look at this. Let's say you do hit 30 meters per second squared. The average person weighs like 100 kilograms. And then let's do it. Because right here, what's the units on this? 1 Newton is equal to 1 kilogram times 1 meter per second squared. Yeah, and check it out. So we're going to find the force in newtons. Alright, more time on the clock. Alright, so we're going to find the force in newtons if we have 100 kilograms. And we're multiplying by 30 meters per second squared. Well, holy hell, that's 3,000 newtons. So you're going to have 3,000 newtons on the human body if you're pulling 3 G's. Now, the human body, you know what I mean? Yeah, it's a surface area. You know what I mean? So you're gonna get this force equally distributed over the surface of your body. You know what I mean? And what's 3,000 newtons? Well, know that that's one way to do it is, well, divide by 1,000. If it's big in newtons, yeah, this is going to be 3 kilonewtons. But even if 1 newton is a quarter pounder from McDonald's, okay, so you would just divide this by 4. But it's easier if you do 3 kilonewtons. And what's 1 kilonewton? It's Mike Tyson. Mike Tyson. How much does Mike Tyson weigh? 1 kilo. He weighs 225 pounds. So that's the other. This is more accurate because if I did up here, it would be Mike Tyson weighed 250 pounds. But no, more accurate. Mike Tyson weighs 225 pounds. Okay, so you have 3 of those. So you got 325 plus 325 plus 325. All right, that's 975. So you got a force of 975 pounds on your friggin' human body. That's why 3 G's is too much. But that's pretty amazing that you could have 975 pounds on your body. You know what I mean? I guess you can bench press through your arms. You know what I mean? Like, I don't know. The average person, less than 200 pounds. Probably less than, some people less than 100 pounds. But there you go. You got 100 pounds there in your arms. And then, yeah, so 975 pounds. That's hella. And the take-home point is that if you have an acceleration, you have a force. Because whatever's moving, that was the other thing. You know, if I said something moves from this point to that point, what do you have to have? You have to have a change in time. We do not live in Back to the Future world. The other thing that has to happen is that if you have an acceleration, if something accelerates from here to here, you know, it's going right here, it's like starting real slow, and then gets faster, and then, so 0, 1, 2, 3, and then gets hella fast, right? What did it have to have? Well, guess what? It had to have mass, little m. It has to have mass. Well, we're not talking about subatomic quarks and, you know, that type of stuff. Anytime you're figuring out an acceleration, guess what? you figured it out for some sort of mass. You know what I mean? Like you just did. You know what I mean? So if you're finding an acceleration, you must have found an acceleration for something that has mass. So that's where we're getting into. And then if you found an acceleration, you know it has mass, well, guess what? You are seeing a force. You just are. There's a force involved. Now, yes, if you're driving down the interstate with constant velocity, velocity is constant, hey, you don't feel a darn thing. But, you know what I mean? You slam on the brakes, hell yeah, you're going to feel the front of your seatbelt. You know what I mean? Whoa. Yeah, hell yeah, you're going to feel it. There's going to be a force. You know what I mean? You are going to go this way with a force. The seatbelt is going to be like, whoa, with the force. You know, I get it. So that's the cool thing. The take-home point for any engineering and physics, especially engineering, like why the hell are you spending so much time on calculus just to find acceleration? It's because it induces a force. And guess what we know about forces is that things break. You know what I mean? If you got a bridge and you put too much force right here because you were jumping up and down and stuff, I don't know, or just a lot of weight, you know, you might break it. And then it's going to look like that. And whoa, people. And yes, so that's why you spend so much time in engineering to get an acceleration. And it's very important to figure out, well, what's an acceptable acceleration? Because the last problem I did, it was something this size. It was a little circle that's about 1.25 inches that spun off axis. So this would be the axis that it spins. And then you have a little drive shaft that's only about that size, maybe 1/8 of an inch. Eighth of an inch shaft going up and down more than an inch. Or like maybe just, let's say an inch. You know what I mean? Just for all intents and purposes. It's going up and down a full inch. 30 times per second. And you have a huge acceleration at the top and bottom as it's changing directions. It's literally 50 G's. So what does that mean? Well, that means, let's just do it. So what's 1 G? Well, that's 10. That's 10 meters per second squared. So what's 50 of those? Well, that's 500 meters per second squared. What's the mass of this shaft? Well, let's just say it's, well, I'll just give you the benefit of the doubt, and we're going to say it's, I don't know, let's say it's 10 grams. That's fair enough. It looks like it's made out of metal, and it looks like it's only 10 grams. And we got to move the decimal place 3 times. 1, 2, 3, and we get 0.01 kilograms. Okay, so now we got our force. Force is 0.01 times 500. And then we get I think we should make it, I don't know, because this is just 1, 2 zeros right there, 1, 2, so you're going to get 5 newtons. Force is equal to 5 newtons. If it's real small, so you actually don't induce a lot of force if this is a real small mass. Okay, fair enough. So if you have a small part that doesn't weigh very much, you actually don't incur a lot of force. Yeah, fair enough. But you're cyclically loading, you know, this, you do kind of, you get fatigue. It's kind of like the coat hanger effect, bending a coat hanger back and forth. But cyclically loading anything, you know, it can take a lot of force, but cyclically loading, it fatigues. So anyway, so I guess I wasn't too surprised about, I thought I was going to be more shocked about this. Let's say it was 0.1 kilograms, and then you're multiplying by 500, you get 50 newtons. Well, that's still just 10 pounds. 10 pounds of force to stop this, and yep. But this part looked really lightweight and fast, or so. I don't know. Okay, so moving on. Alright, so we figured out why you want to find acceleration, because it induces a force. And you just saw that humans can only do 3 G's because we weigh a lot, 100 kilograms. There's going to be a hell of a lot of force on us that's hard to withstand. Alright, well, let's do one. So, they just give you the acceleration. Alright, let's just say they give you this acceleration. The acceleration is a function of just a constant, a spring constant, divided by the mass times the position right here. So if the position is 0, the acceleration is 0. Fair enough. And yeah. Because a spring, let's say it's just in its neutral state. There you go. There's this where the spring wants to be. X is equal to 0. There is no acceleration. Acceleration is 0. But you take the spring over here, hell yeah, you're going to get an acceleration back negative. You know what I mean? So if your position is positive, your acceleration, hell yeah, your acceleration is back negative. Now if you squish the spring this way and you take your position negative, well, yeah, your acceleration is going to go, if your position is negative here, well, it's negative times negative, your acceleration is positive. Okay, so yeah, booyah. So this is the tricky thing about engineering and physics, is just like you have to have like a certain amount of knowledge to be like, oh, I can set up an initial condition, you know, just where it's neutral, and then, but with all that rigmarole of figuring out why acceleration is important, because we can just write it in. We can do acceleration is equal to F, excuse me. So we got F equals ma. We just found acceleration. Well, that means acceleration is equal to F over m. Well, guess what? Look at that. There's the mass right there. So it looks like the force is equal to negative kx. And this is the force of a spring. You take the spring constant, so if you have a spring that's this big, and then you, with the length, let's say just a length, and then you double the length. Let's say it's just 5 inches, and then you go to 10 inches. Well, let's say if you do go to 10 inches, there's 20 pounds on the, so then you could actually, and we got to convert to newtons, and we got to go meters. So we're going to go, and we're going to do 4 inches, because that's this is going to be 0.1 meter. That's 4 inches, 0.1 meter. And that's the tricky thing about American engineering, is you have to convert everything. And then we're going to be satisfied if this is 100 newtons, which would be 25 pounds. Okay, fair enough. So we're going to go 100 newtons here, and we're going to go 0.1 here. So what's the spring constant? Well, won't we do 100 divided by 0.1? 100 divided by 0.1? Hell yeah, our spring constant is 1,000. Now 1,000 what? Well, our force is 100 newtons equals to negative our K times 0.1 meter. And we know that force in newtons is equal to mass in kilograms times 1 acceleration in meters per second squared. So we know that this side has to be equal to kilograms meters per second squared. We're given a meter, so this has to be in kilograms per second squared. So our spring constant is kilograms per second squared. Cool. You know what I mean? So there's a lot of things. Any math problem you do, it's like there's so many basics that you can do that will really help you out. That if you don't do them, you know what I mean? The second they ask for them on a problem, you're just like, what the hell are you talking about? Like, what's the units on the spring constant? Because they'll just briefly cover that at the very beginning of a textbook. Be like, hey, these units are important. Okay, so we got the spring constant. And we got the acceleration. So really, we can just write it in. We can go A is equal to negative 1,000 kilograms per second squared divided by mass in kilograms, and so that'll cancel out, times your position in meters, and then you'll get meters per second squared, which is the units of acceleration. Okay, sweet deal. But that is literally not what they're getting at. They're going back to saying, hey, what's acceleration? Acceleration is change in velocity, change in time. Okay, so they're going to do that. And right here, do they do that? No, they need to do something a little bit different. Why? Why do they need to do something a little bit different? Okay, it's because this. Well, let's go back to A equal A spring constant x divided by m. It's because what we need to know is we need to know at any given point where the hell this thing is. So we need to know, we got the equation for acceleration, cool, but we need to know velocity and we need to know position. Just like this was 9.8, we took the integral of it, we got 9.8t, we took the integral of that and we got 4.9t squared. We basically need to do the same thing. And so right here, you need to take but this acceleration is not a function of time. Like we just said that this acceleration, we're just like, well, let's just throw a t naught in there, and it is a function of time. Great, okay. And but this acceleration, look at this. The acceleration, well, it's actually a function of position. So we need to treat it like acceleration is a function of position. So then when we go to integrate, we integrated this with dt with respect to time. So what we would have to go, acceleration is equal to the integration of 9.8 position to the 0 dx. And then we would get velocity as 9.8 x to the 1 plus c. And is that even right for that? Holy Toledo. I would have to go back to see what we actually did for, well, because we got this as t is equal to x over 4.9 square root. So you could go back and say velocity as a function of position is 9.8 square root x over 4.9. And then, yeah, wouldn't that give you the velocity as a function of x? Yeah, so right here we want to find the velocity as a function of x, as a function of position. This was the velocity as a function of position. So the velocity as a function of time is real simple for this one. The velocity as a function of position is actually pretty complex. And then that's going to be the issue with all these physics problems where you're just like, yes, we know the acceleration. Why? Is because we know the force. Like the problem in the book is like, let's say you got an air bubble stuck to the bottom of like water, and the second it pops up, it's got velocity is equal to 0. But guess what? Right here, it's going to have velocity as constant. Why? Is because terminal velocity. So a lot of things don't just accelerate into infinity. You know what I mean? Given enough time. Like even a skydiver hits terminal velocity at 120 miles per hour. You know what I mean? 260 meters per second, pretty fast or whatever. It's the other way. It's the other way. It'd be 200 meters per second, terminal velocity of a skydiver. And then because the force on this, well, your acceleration, well, it's going to be like 80 minus, you know what I mean, 4 times your velocity. That was one of the problems in here. So if your velocity is 0, hell yeah, your acceleration is going to be real fast. But then once your acceleration, your change in velocity is real fast, your velocity goes up. So right here, if your velocity goes up, well, 80 minus anything is going to be less, so then your acceleration goes down. Okay, so that's kind of the common, like every time you do these physics problems, especially the ones that do differentiation, And then what's the limits on here? Well, if you have a 0.1 meter spring, a 4-inch spring, like literally, how far can you pull a 4-inch spring? I mean, maybe you could change its length. If X is 0 at 4 inches, you could change it to 8 inches. You know what I mean? Be a total of like 12-inch spring. You know, but at a certain point, you can't pull springs more than they don't even act. You'll just sprung the spring. So all these problems are just like, yes, you know, the acceleration is not infinite because your acceleration is only going to be, you know, that many inches and stuff. Just like this one, your acceleration is bound by terminal velocity. A fallen skydiver, acceleration is bound by terminal velocity. Alright, new battery, we're still going to go for it. Alright, hell yeah, we're back. But man, I need to do something real fast because that sine of x was just driving me nuts. So we're going to go sine of x into our calculator and we're going to go mode degrees. We're going to graph that action. Yeah, I guess we can. Degrees, you know what I mean? Then you got value, you know what I mean, 90 degrees, you know, 45 degrees. Whoa, zoom out or something. Oh, there you go. Value 45. Okay, there you go. Value 90. Okay, perfect. All right, so there you go. So, this is the graph of sine. Whoa. Value at 0? Oh, that's cosine. Yeah, we want sine of x. Graph that. And it's going to throw me for a loop because the colors are backwards. So we're going to go sine x and then cosine x. Oh, man. And then we're going to go value 90. Okay. Value 180. Oh, okay, value 0. Oh, we got to zoom out. There you go. Oh, we should do zoom fit. Sorry about this. All right, zoom fit, zoom 0. Zoom fit that in there. There you go. All right, so we'll get them both. Excellent. So the blue one's sine, and check it out. So let's see. Oh. Well, no, let's friggin' do this. Yeah, the blue one is sine. You got sine x, you know what I mean? And that just looks like just a graph like this. Okay, perfect. You know what I mean? And we already did that. So the area under this curve, oh, well, that's the thing, is like a sine x don't start at 0. You know what I mean? So, it's so hard, like yeah, so that's where I don't get the, you know, the integration of sine x is the area under the curve, but it looks like there's 0 area here, so, but no, it's gonna, you can't do that, because you would have to add all the area up prior, you know what I mean, to that point. And I don't know, I think it gets into an infinite room situation, the infinite hotel situation of where the hell do you start the integration of, you know, where do you start that first area? You know what I mean? Is this area negative? Is that where you start? Or do you start here and this is positive? I have no idea. But the slope of sine x, see there's a huge slope here. Oh no, it's the change. Okay, perfect. Yeah, this is the deal. So the change in sine x, that is all the differentiation is. It's not with respect to x. You don't divide by x again. So look at this. So because I know when you have an inflection point like here, your change is 0. You don't have any change in you're changing. Okay, so if this is your position, your position function is sine of degrees. Okay, so then your dx, your change in position, as a function of d theta, with respect to theta. You know, if your angle's changing constant, if your angle is going from 1 degree to 2 degrees to 3 degrees, okay, your change in x, well, is going to be so where you have an inflection point, you're almost 0. So your change in x is right here is just like almost 0. But then right here, your change in x is so let's do that. Let's go sine 1 degree, store it as b, sine and then go sine 0 degrees. Well, that's 0. So there's your change. It's 0.017. And then let's go sine 2. We're going to store that as C. Sine 1 stored as B. Whoops. Sine 1 stored as alpha B. 0 stored as alpha A. So now we're going to get alpha C minus alpha B. Store that as alpha E. Alpha B, we're going to store that as alpha D. So now we're going to go alpha E minus alpha D. And yes, you have a very small change. So this is, and it's a negative change. So we're going to go back here. Yeah, right here you don't have any change in x. That's why here. And then right here it's a negative change until right here. Now you're going to have a positive change in x. So value 90. So now we're going to go sine 90, sine 91, and then sine 92 degrees. Okay, we're going to store this as A, B, C, and then we're going to do this one minus this one, and then this one minus this one. We're going to store this as E, D, and now we're going to go E minus D. So this is your x2 minus x1. This is your x final minus x initial. But this is your dx. This is your change in x, dx. Okay, so we're going to go sine 90 stored as alpha A, sine 91 stored as alpha B, sine 92 stored as alpha C. Now we're going to go D minus A, alpha B minus A, alpha B minus alpha A, and we're going to store that as D. Then we're going to go alpha C minus alpha B, alpha C minus alpha B, and we're going to store that as alpha E. Now we're going to go E minus D to get this. Alpha E minus alpha D. Oh, damn it, it's still negative. And it's negative, it's a little bit more. It's negative 3 times 10 to the negative 4. We're going to go sine 45, sine 46, and then sine 47. Same thing. Sine 45 stored as alpha A. Sine 46 stored as alpha B. Sine 47 stored as alpha C. Alpha B minus alpha A stored as alpha stored as alpha D. Alpha C minus alpha B stored as alpha E. Now if I just had Excel, I'd be able to do this real fast. But now we're going to go alpha E minus alpha D. And then yes, we get negative 2 times 10 to the negative 4. So you get a little bit less change than that. Man. Alright, so this isn't getting me any closer to figuring out, like I swear I'm making mistakes in here of exactly what, yeah, I mean, what's sine theta d theta? Well, what's or do you do this? Do you go d theta sine theta? Is that how you do a differentiation? Because if you were integrate sine theta with respect to theta, change in theta, this is your area. Okay, so now I get that. I get how you're like, oh, okay, here's your position, and then here's your change in position. Like, let's say it's a big change in position, and now you're just going to take this value times, well, this is your d theta. So you're basically just taking this area, and you know, if you're right here, you know, if you take a little slice, you know, and you're taking it x 222 minus x 221, then you're going to get like an average. Oh, even here you wouldn't do x 222 minus x 221. For here you would go x 222 plus 221 divided by 2, because you want the average right here. So you're going to take the average and then multiply it by d theta. You know, let's say it's just 1 degree. You're going to take a 1 degree slice and then figure that out. So let's do that. Let's so we can integrate. But then it's just going to be this slice. That's the area that you would take. It would be like integrating from, let's say this was 46 degrees to 47 degrees. You know, you'd be integrating from 46 to 47 of sine theta d theta. Well, yeah, then you would actually figure out, you know, whatever the integration is. It cosine? Is it negative? I forget. You know, who knows? Who cares? Because we want to solve this practically. But even if you would actually have to well, the integral of sine theta d theta. Oh, maybe I am confusing myself, and it is. It's just you do just take this value. Now I forget what an integral is. I mean, but that's why I'm doing this, because you're just like, whoa. It's so interesting how, unless you get over this hump of you're just like, oh, I can explain it to you, and because yeah, now I'm forgetting. Yeah, it's perfect. You know, go through college and then forget what a differential equation is. Forget what an integral is. But then I'm going back and actually showing. So now we're going to get back to it. We're going to throw some more time on the clock. All right, and I got to get on with my day. So let's just do this problem. And I think we need some of our, so we said that v is dx dt. Definition of velocity, change in x, change in t. Definition of acceleration, change in velocity, change in time. Okay, and then we can rearrange those. Okay, we also know, I don't think we're going to use it, but chain rule, dx dv times dv dt is also something that we might use. But in a sense, these problems are just all F equals ma. And what you're trying to do is you're trying to isolate ma, or you're trying to isolate a. So you're going to try to find a function for the area, and guess what? If you do isolate this, your function for the area has got to be something like function divided by mass, and that's what we get. The acceleration of a spring is equal to negative k kx divided by m. See, so this is your force. If you want to know the force in a spring, you can use a spring as a force. You just need to know your spring constant. And then, hey, I put this jug of water on it and the spring lengthened 4 inches. Well, if you know that, or like 0.1 meters. And like I said, we can do that. If, well, let's go, yeah, F equals ma. And we said the force, we said, so yeah, F is equal to, you know, spring constant times x. And we said the spring constant was 1,000 and our x was 0.1. So it looks like we got 100 newtons, which we said is 25 pounds. So yes, this is how you can figure out F equals ma to figure out the force. So yeah, all these physics problems, your acceleration will have to do with a force. It's usually friction. You know, like whether it's the air bubble going on, there's a lot of friction on this air bubble. Whether it's a person falling through the sky, a lot of friction with drag. And that friction is the same thing as a force. So if you're finding a force of, you know, due to friction or something, if you are putting a force on an object, guess what? You had to put a force on something with mass, and now that mass will have a change in velocity. It'll have an acceleration. And like we said, the second something hits like a solid surface and you have no more movement, your velocity is equal to 0, you still have an acceleration because F equals ma. Your acceleration goes to 0, but what that means is that the ground is actually pushing again, like this is pushing down because it has force pushing down, and then the earth is also pushing back with a force. We're going to see if this is just spam. Hell yeah, it's just spam. And this is so brief. I just briefly covered, but this is dynamics. I mean, this is statics and dynamics. They teach you statics first, but they really should teach you dynamics. The fact that something has an acceleration, whoa, just by nature, because it has a mass, and they should call it FAM, F equals AM. FAM, I don't know, but yeah, F equals MA. If something has an acceleration, well, it had to have a force on it. And but if it stopped, if it has no velocity, that acceleration still exists because your forces are equal and opposite to make this go to 0. So if you have the Earth down here and then a fallen object falling towards the Earth, well, guess what? That falling object has a mass. Gravity is the acceleration. So yes, you have a force equal to the mass times the acceleration on that. And it's falling because it's basically the same thing as you putting a force. Like you putting a force on this, a constant force. Now, it's not just I take my hand on it and I push it down real fast and then it's falling. It's the Earth is actually tugging on this thing. You know what I mean? Because the Earth has got gravity, and the Earth is literally just a constant force. And yeah, perfect. And the other thing you can do is figure out the velocity, because acceleration is change in velocity, change in time. But there's going to be a point where this thing hits the Earth, and the acceleration will actually go to... Oh, this is so interesting. This is the most confusing thing. So you have F equals ma, and A is the acceleration of this box. So we're going to do this. But guess what? The force on this is equal to the mass times gravity. So then you'll get something like this. The mass of the box times the gravity of the Earth is equal to the mass of the box times the acceleration of the actual thing. And of the actual box. And so if you want to find the acceleration of the actual box, you will you know, get like terms on one side, mass of the box divided by the mass of the box, those cancel, times gravity. Great. So the acceleration of the box is the Earth's gravity, g, which is 9.8 meters per second squared. But when it hits the Earth, this acceleration of the box, well, it's 0. And but you still have the mass of the box being influenced by gravity. But if this side is equal to 0, something else has to equal out this. So you have to, you know, this has to be equal to the, you know, like minus the actual force of the Earth pushing against this. So yeah, if this is pushing down, and we're calling that positive, the Earth, we'll call this force of E. The Earth has to be pushing up. Okay, perfect. Okay, anyway, we're gonna move on. But for these physics ones, I think the trickiest thing is that both these sides can be very similar. So even though you got acceleration here, this is the sum of all the forces. So it's a little bit weird because mg can be over here. Wait, I thought this is the total acceleration. So if you got like a person falling through the sky, well, hell yeah, they got mg. That's their acceleration or the force on them is there's a force from the Earth, and then there's also a frictional force, maybe due to their velocity. So their frictional force due to velocity, so this is the frictional force due to gravity. Frictional force due to velocity is going to be, you know, some sort of stupid constant, and then times velocity. And that's going to be upward. So it's going to be positive. This is going to be downward. And now you got F equals ma. Well, you have to sum all these forces. So you're going to have negative F, the force of gravity, which is just the mass of the person times g. So you're going to have negative mg plus maybe a frictional force up. So that's going to be a constant times the velocity. So you're going to figure out what the hell the velocity is. And then all that is going to equal to the mass times the acceleration. Or you know, the same mass over here, you're a person. But that's going to be your acceleration. But hey, now because of that, because I dropped out of the sky, out of a plane, and I want to know, let's say I want to know my velocity. You know what I mean? And then I want to know my position, given this equation. How the hell do you do that? Well, like we said, you isolate acceleration. So now you got acceleration is, I don't know, you know, this divided by m. And now you got to integrate acceleration to get velocity. And what are you going to integrate in acceleration? Or do you need to integrate acceleration with respect to time? Because you want to know the velocity at any given time interval. For each second, you want to know the velocity as a function of time. You know, maybe you want to do that. So you got to integrate with respect to time. And then who the hell knows how to do that? You know what I mean? And then you would actually integrate again with respect to time to get the position function with respect to time. And this will have a constant velocity. Well, your initial velocity might be 0. Your initial position might be 0. So it kind of goes back to that basics of how I dropped the rock. We're going to do this one, and hopefully we'll finish up. Alright, hell yeah, we're back at it. And yeah. Anyway, like... they kind of showed you in 2 parts how to actually do this in the textbook. Well, screw that. We're not going to do that. Anyway, that's the whole point. It's just like, oh, okay, we already did like a bunch of things to be like, oh yeah, all these things are the same. Oh, I need to get my timer right. Alright, hell yeah, last push. Last 20 minutes on the clock. We're going to do this. Okay. So F equals ma, and they have acceleration, negative k mx. Okay, cool. So we have x, and we have acceleration as a function of x. So just right off the bat, this is acceleration as a function of position. It's not acceleration as a function of time. Okay, cool. So if we integrate acceleration, we can get velocity. Velocity is integration of acceleration, but we'll have to integrate maybe with respect to position. And then we'll get velocity as a function of position. Okay, alright, so, and that's fine, because on springs, you know, a spring is something where you're just like, okay, I can visually measure the spring going from here, and now it's to here. And I'm going to measure this x distance. And guess what? What I want to know is I want to know, oh, and let's say it's going back and forth. It's oscillating back and forth. But I can take a picture of it in time and be like, oh, well, when it's at this position, I want to know what its velocity that way is. Velocity that way. You know what I mean? And so it's going to reach some sort of max, and it's going to reach some sort of minimum. Hey, velocity 0 at those 2 points. So just any physics problem, if you're able to do this, it may be advanced level, but you get a problem, you're just like, oh, this spring's springing back and forth. Guess what? Velocity over here is 0. Velocity that way is 0. So, but what's the max change in, so your acceleration is max when it's changing direction. You know what I mean? You're changing your velocity the most right when the velocity is 0. You know what I mean? And so that also needs to be known as well. Okay, so I think we got it. So we want to know we want to see where the position of this is, and then just kind of know its velocity. And what do we also want to know? Well, we also maybe and we might want to know its position with respect to velocity. I think that's what they get down here. They're just like, well, can you actually figure out where it's going to be if you know its velocity? Yeah, fair enough. If this was acceleration with respect to time, and maybe we could do that. Maybe there was a way to figure out, if we could figure out its acceleration with respect to time, and then we could find this velocity with respect to time, and then at any given point we can find its position with respect to time. I don't think you can do that for this one. Alright, so F equals ma, and we got our acceleration function right there. I think we just have to write all that crap in, you know, of like what's the definition of velocity? Well, that's change in position, change in time. Okay, got one. What's the definition of acceleration? That's change in velocity, change in time. All right, got another one. So right here, you have acceleration. Look at that. So accelerate, you could just write right there. You could go dv dt is equal to negative x m over x, but is equal to. But does this really help us? Not really, because so you have a function. Let's say you have a function that's just x squared, and we got to integrate that. Integrate the function f squared with respect to dx. So you need this dx, and then yeah, if you have this change in x times the function, great. Then you can go x 2 plus 1 divided by 2 plus 1 plus c. And then you get x to the third. You get 1/3 x to the third. Great. That's the integration of f of x dx. And I really don't even, you know, integration is area under the curve. So you need to take the value and then multiply it by the little slice. So you're trying to find area. So cool. And in a sense, we're given acceleration. So we need to integrate acceleration to get velocity. Integrate velocity to get position. Okay, cool. We got it. But you can't, if here's your function, you need to integrate this function and then put a dx right here. So you need to figure out how the hell to get a dx right here. And you just put a dv and a dt. You can't do that. You know what I mean? It don't make sense. So now we need to figure out how to get an x right there. And we're just going to figure out what the hell they did. Oh, perfect. So they do kind of use the chain rule. So they take this one. You know how we said, I don't know, v is equal to dx dt? Perfect. I'm going to like this one because this one I never figured out. But you can go dx dv times dv dt. Cool. But what they did with acceleration is go definition of acceleration, change in velocity, change in time. But that's also dv dx times dx dt. And guess what? Guess what? dx dt. So this is classic chain rule. What is dx dt? Well, we said change in position, change in time. That's the definition of velocity. Perfect. So you're gonna hook this right into there and put a v. Just take that spot. So we're gonna go dv dx and then put a v here. Perfect. So now we have instead of what was our initial thing? Oh damn. So right up here, your acceleration is negative kx divided by m. This is the x thing that we want to integrate. But guess what it is? This is v dv dx. Whoa, there's our dx term. Hell yeah. And then we got negative kxm. So we're going to kick the dx term right up there. Perfect. And we'll just do that right here. And then you got v dv is equal to negative kx dx. Perfect. So now you can integrate something. You can integrate this side with respect to x, and you can integrate this side, and that's going to be your little slice of v. So you have like two functions. You have this function for velocity. You're going to pick the velocity right there, take a slice of it, and find the area. And do that for all the little sections. And you're going to get a whole different equation. And then right here, you're going to do the same thing. You got a function going negative, and you're going to take a slice, and you're going to get dx it. So you're taking the area. But anyway, now you're able to do it. So integrate v dv. And then, okay, so let's integrate x squared dx. Okay, well that's x to the third divided by 3 plus c. Okay, integrate x dx. Okay, that's x to the 1 plus 1 divided by 1 plus 1 plus c. So that's basically x squared. Okay, plus c. Okay, so yeah, that's what we got right here. Integrate v dv. Well, that's integration of v to the 1 dv. So let's spell this out. This is the integration of the constant x to the 1 dx. So your integration is going to be v to the 1 plus 1 divided by 1 plus 1 plus c is equal to negative kx 1 plus 1 divided by 1 plus 1 plus c. Just basic integration. So now we have v squared divided by 2 plus c is equal to negative kx squared divided by 2 plus c. What's our initial condition for this spring? Let's say it's just in neutral. X is position 0. Well, what's our initial velocity? Well, that's the crazy thing. Is actually this side will not be okay. This says the constant of integration can be evaluated from the initial condition of velocity is equal to v naught when x is equal to 0. Oh. So you actually go back to oh, do you go back to this one? Holy, how the hell did they do that? Oh, and we forgot our m here. This is divided by m. See, just a lot going on. And but yeah. Well, let's write it how they got it. They got v squared over 2 oh, and I guess these constants just add up to one side. You know what I mean? I guess it ain't no thing but a chicken wing. And, but now you got plus c. So right here, you have initial condition. When x is 0, so if this is 0 right here, guess what? You have to satisfy this equation. So c is going to be, c is v squared over 2. If your initial position is 0, your velocity initial, they call it v0, is equal to, or they call this v initial. Your initial, because this is a function, but this is just an initial velocity. Alright, so let's get another sheet of paper, put some more time on the clock. All right, I'm still with you. Okay, here we go. So let's do that all again. Well, what the hell you were saying? You were saying F equals ma, and they give you the acceleration. They're always going to give you the acceleration equation. And again, that's what we want to know, because we want to figure out we're not going to kill people if it's an amusement park ride. We want to make sure the acceleration is less than 3 Gs. We want to know, and then there's a force involved too. Maybe we don't want to rip our springs apart, and we want to, anyway. So acceleration is negative a constant times x divided by m. And we said, hey, if F equals ma, that means that A is equal to F divided by m. And booyah, there's our m, and then, so this must be our F. There you go. And then we're going to integrate acceleration to get velocity. Okay, so let's get back to there. And, and then a definition of velocity is change in position, change in time. Definition of acceleration, change in velocity, change in time. But you can use chain rule to say definition of velocity this is change in velocity, change in position, times change in position, change in time. And we already said that, yes, you can put a V right there. So cool. So acceleration is dv dx v. Okay, so now we're going to put this into this side of the equation. So we're going to go we're going to go dv dx. This is acceleration, is equal to negative the spring constant x divided by m. I'm not going to forget about the m. And then perfect. So now you got to bring this over here because you want this dx right there. And then yeah, you got your v terms over here, and then you'll have your x terms. So then you're going to go v dv. I just switched these around just so you see, is equal to negative x. The spring constant. I'll just say the spring constant is negative. X dx. Don't forget about our mass. Integrate both sides. Hell yeah. Then you got v squared over 2 is equal to spring constant. X squared over 2 times the mass. Plus the constant. Now anytime you integrate, every time you see this word c, I think they should turn it to this. They should say plus I. If I had to rewrite math, I know I gets used a lot for other things, but this should be plus I because it's your initial condition. And yet maybe you don't. Maybe you use your final condition. You know what I mean? At some point, when x goes to infinity, terminal velocity. You know what I mean? When your position fall into the bottom of the ocean. When your position just goes to infinity, yeah, you can satisfy your initial condition. But usually this C, your C is your initial condition. Initial. It might be your final, if something goes to infinity and then kind of balances out. But that's a freebie on me. So you'll go here. X, my initial X is going to be 0. We're just going to figure out where the hell neutral is. It is moving back and forth, I swear to God. If the block is launched at x equals 0, yeah, it's going to be launched with a velocity. I haven't even read the problem, who cares? So yes, it's in the spring is in a neutral position, but you're just initially launching it with a velocity. So within a split instantaneous second, you're inducing a quick velocity, and then you're letting the thing go back and forth. So if this is 0, well, hell yeah. That goes away, but C has to satisfy the equation. So C is equal to your, and we're just going to do velocity V naught. That's what they do in the book, V naught. And just know that V naught is equal to VI, which is equal to velocity initial. Your initial velocity. Perfect. Divided by 2. That satisfies the equation. Well, now the equation is V squared over 2, negative, or the spring constant, x squared over 2m plus v naught squared over 2. So this is a constant, but this is actually an equation because this is the velocity. So yeah, velocity with respect to x. It's a function. It's a velocity function. You throw in the position, you get the velocity. That's what this is. That's what a function is with respect to x. Velocity with respect to time. Hey, I know in 10 seconds from now, I want to know what the velocity is. Well, we don't have that. We have, hey, if you measure over 2 inches, I can tell you what the velocity is going to be. And if it's springing this way, it's going to be velocity 0 at the max, goes to the min, it's going to be velocity 0, and then it's going to be fast in between. Okay, and we're going to simplify this because we can get rid of these 2's. So, you know what I mean? So then we got v squared is equal to the spring constant, don't forget about the mass, plus v naught squared. Now, what the hell do they want? Oh yeah, like I said, you want this velocity with respect to x. So now we can just write this in. It is the velocity with respect to x. We want to isolate that. So it looks like we have to take the square root of that side and the square root of that side. That's what they do. And then they just get it. Because you're taking the square root, I guess that you have to do a plus and minus. So we'll just do that. So we're going to get that velocity is a spring constant, x squared, m plus v naught squared, all square root, but plus and minus. Because, yeah, right here, you're going to say this is positive velocity, but then on the way back, it's going to have negative velocity going back and forth. Cool. And it says, the position of the block when it first comes to rest is found by setting... if this is a function of velocity, you want to know when the block actually comes to rest. Because I think there's a coefficient of friction here. Well, the spring has a spring stiffness. Oh, I thought you'd have to induce some... I thought it was an ideal condition. But yes, if you have mass, you definitely have a normal force, and then you got a frictional force. But it's a frictionless plane for this one. Oh. The position of the block it first comes to rest. No. There's a, yeah, this is a frictional, it's going forever. It's going back and forth forever, but it's going to hit this maximum. It's traveling this way, and the spring is going to start pulling it back. So we want to know when, at what distance of x is the thing actually going to stop and then start going the other way. So that's what you do here. And so what you'd want to do is you'd want to find when velocity is 0. So you just put a 0 right there. You go plus or minus the square root of negative x spring constant m plus v naught squared. But guess what? If this is 0, you can square root both sides. Square root of 0, so it gets rid of this. You can instead of subtracting this over here, I would take this way. That gets rid of that sign. So now you got spring constant x squared over m is equal to initial velocity squared. All right, cool. So now you can take and what do we want to know? We want to know the position where the velocity stopped. Okay, so we're going to kick the m up there, k down there, and we're going to get x squared is equal to m k v naught squared, and now we're going to square root both sides because we want just the position where the velocity comes to a stop, and that's going to be the mass of the stupid block divided by the spring constant, and you're going to have to take the square root of that, but the square root of this thing is just the initial velocity, so booyah. So then you get exactly what they got here. And then there's a note. It says with this initial condition, we can write this as that. If we plot v versus x, called the phase plane plot, the result is ellipse because the plot is a closed curve. The motion of the block is oscillatory. The motion repeats itself. Yeah, and the next page is just a picture of a stupid ellipse that looks like that. Who cares? I think this was the take-home point. But mainly, it was the first time using a damn chain rule. You know what I mean? Yes, you can say that velocity, change in position, change in time is equal to change in position, change in velocity times dv dt. Hey, so that's velocity is equal to dx dv, and then look at that. That's the definition of acceleration. So you can use the chain rule of velocity to get to something with acceleration, but what they did is you use the acceleration, dv dt. Well, that's dv dx, dx dt. See how these cancel out and you're just left with dv dt? But booyah. But you know that dx dt, definition of velocity. Definition of velocity, change in position, change in time. Hell yeah. But it's so crazy how it's just like, whoa, you don't see the basics here. All you see is high-low. I don't know how to say hieroglyphics, but yes. All right, and then yeah, throw a V in there. So that's what we did. We did the chain rule once, and it's useful. So it's useful when integrating, but there's about 20 more of these in this book where yeah, but the basic is the same. You're given the acceleration. You need to integrate. Integration sucks and it's hard, but you need to get a dx over here. Let's say acceleration was like velocity and then and velocity times time. Wait, is that the definition? No. Yeah, well, what if acceleration is equal to velocity divided by time? So that's the acceleration as a function of time is equal to velocity divided by time. Meters per second squared. Yeah, that's actually the definition of and velocity is a function of time. I think I'm just rambling. I think you can turn this video off, but well, whew, oh. No. I think we're onto something here because we're gonna keep going until we can't go no more. So acceleration, velocity divided by time. Well, isn't that acceleration is equal to velocity divided by change in time? You know what I mean? Hell yeah. Definition. Well, I guess the definition of acceleration is change in velocity, change in time. Acceleration at any point is if you know the velocity divided by the actual time it took at that point. So yeah, so this is true, and this is true. Well, what were you saying? You have the acceleration is like a 10 over t. So as time goes on, your acceleration, so as t goes to infinity, your acceleration basically goes to zero. Fair enough. But at the very beginning, when time is equal to 0, your acceleration is just infinite. I don't think I like that one. But anyway, I think I'm done. We did the chain rule once, and it'll take me about 1,000 more of these videos to actually, whoa, you know what I mean, make quality content. But you get to see the process. If I ever start making quality math videos and engineering videos, you'll be like, whoa. Yeah, I see where you started. I see where you started. And I see how it's difficult to teach. But it's good. It's actually, so this is a method. It's just like, I'm not to the point where I can teach this subject, but pretend like you have to teach it and learn it at the same time. That is exactly what we're doing. And then so, things that I do know, that's the thing. If we're talking about numbers, I can be like, hell yeah, 2 plus 2 is equal to 4. You know what I mean? But let's say I don't know what 2 times 2 is. And I have to explain that. And it's like, well, isn't that equal to 4 too? And I'd be like, well, what's going on here? I'd be like, well, you have 2 little dots, and then you got 2 little dots. And guess what? How many dots do you have? 4. But what the hell's going on here? I say you have 2 little dots, and then does this mean you just have another 2 dots? Well, no, it says, you know, let's say this is a group of dots, and now I have plus. Holy, my camera went out. Anyway, it means you got 2 groups of dots. You know what I mean? So you got to count up these, and then you got to figure out, well, how, you know. So it is different. And my camera overheated. I don't even know what the hell I was talking about, but it was all related to what we're doing here, becoming better teachers. Oh yeah, it's like, yeah, you know something, but then maybe there's something you don't know. You know what I mean? How do you get there? And can you start teaching something you don't know? Well, that's these videos. Whoa, looks like you're teaching something you don't know. So it's just real fascinating seeing how I can grow as a teacher. Anyway, alright, I'm done, and I got to do some actual real paid work. You know what I mean? Do the thing I'm good at, mowing lawns. Alright, so that's a video.